Hey, sleepers! Tonight, we're journeying into the ticking heart of a quantum puzzle. Imagine a diamond, perfectly clear. But inside, deep within its crystal lattice, a tiny, invisible clock is ticking forever, out of sync with our world. A heartbeat with no heart. It pulses with a rhythm all its own, a secret timekeeper in a world of silent, ordered atoms. So before you get comfortable, take a moment to like the video and subscribe. It helps us continue to bring these quiet explorations to you. We love to see where you're all listening from. Let us know your city and what time it is there in the comments below. It's a wonderful way to feel connected, all of us listening together in the quiet of the night. So close your eyes, take a deep breath, and get ready to drift off as we explore the impossible crystal that ticks forever. Let's begin our journey not with a crystal, but with something much more familiar. Picture in your mind a simple, beautiful snowflake, or perhaps a honeycomb with its perfect, repeating hexagons. Maybe you're thinking of a salt crystal, a tiny, perfect cube you might see if you look very closely at the salt in your shaker. These are all crystals. They are nature's expression of order. Their beauty comes from a simple rule, a pattern that repeats. It repeats. If you move a little to the left in a salt crystal, you find another atom in the exact same arrangement. Move a little to the right, and there it is again. Up, down, forward, back. The pattern is the same. It has what physicists call spatial symmetry, a repeating pattern across space. For centuries, we thought this was the only kind of crystal that could exist. A crystal was a thing of space, a static, solid, beautiful object. Now, imagine a mind big enough and curious enough to ask a simple yet profound question. If a pattern can repeat in space, could a pattern also repeat in time? This was the question that the brilliant Nobel laureate Frank Wilczek asked himself in 2012. He wasn't just daydreaming. He was thinking deeply about the fundamental symmetries of our universe. Symmetry is a huge deal in physics. It's the secret language that tells us how the laws of nature work. The idea that if you do an experiment today, you'll get the same result tomorrow is a kind of symmetry. It's called time translation symmetry. It means the laws of physics don't change over time. They are constant, dependable. But Wilczek wondered, could a physical object, a piece of matter, break that symmetry? Not by changing the laws of physics, of course, but by having its own internal clock. Could a thing exist that has a repeating pattern in time, just as a normal crystal has a repeating pattern in space? He called this theoretical object a time crystal. What would that even mean? Let's imagine it together. Picture a ball resting at the very bottom of a perfectly smooth, round bowl. This is its lowest energy state. Physicists call this the ground state. The ball has nowhere lower to go. It has no extra energy to move. It is perfectly still. According to the laws of physics we've known for centuries, this is what all things want to do. They want to settle into their ground state and stay there. A hot cup of tea cools down. A spinning top eventually stops spinning. Everything seeks rest. Everything seeks its ground state. Wilczek's idea was radical. He proposed that a time crystal, even in its ground state, its lowest possible energy state, would still be moving. It would be oscillating, ticking, pulsing, forever. Not because it had extra energy, but because motion was its fundamental nature. It would be like finding a ball at the bottom of a bowl that just kept rolling back and forth, from side to side, without anyone pushing it and without ever slowing down. It would be a clock that never needs winding. A heart that beats without life. This sounds impossible, doesn't it? It sounds like it breaks a very, very important rule, the law of conservation of energy. You can't get something for nothing. You can't have motion without energy. A machine that runs forever without fuel is the stuff of fantasy, a perpetual motion machine. And physics is very, very clear that such things cannot exist. They would violate the fundamental laws of thermodynamics, the rules that govern energy, heat, and work in our universe. But Wilczek was clever. He argued that a time crystal wouldn't be a perpetual motion machine in the way we usually think of it. You couldn't harness its energy to do work. It wouldn't power your car or light up your house. Its motion would be contained, a closed loop. It's in its lowest energy state, so there is no energy to extract. It's like a person pacing in a locked room. They are moving, but they aren't going anywhere or doing anything useful. The motion is just there, part of its being, a feature, not a bug. So the idea was born. A new state of matter, a time crystal, a structure that repeats in time just as a normal crystal repeats in space. It would be in its ground state, yet in perpetual motion. A quiet, orderly, ticking object that followed a rhythm all its own. It was a beautiful, mind-bending idea. And as with any beautiful, mind-bending idea in science, it immediately invited a great deal of scrutiny. The conversation was just beginning. Imagine a grand, quiet library, the kind with towering shelves and the gentle smell of old paper. A new book has been placed on a central table, a book full of strange and wonderful ideas. Scholars from all over come to read it. They read it carefully, they ponder its words, and they discuss it in hushed, respectful tones. This is what the world of theoretical physics is like. It's a conversation, a debate, a collective effort to understand the universe. So when Frank Wilczek published his idea about time crystals, the other scholars in the Library of Physics opened the book and began to read. And some of them, very brilliant scholars, found what they believed to be a problem. In 2013 and 2014, a few years after Wilczek's proposal, papers began to appear with titles that were, in the polite language of science, a firm no. Physicists like Patrick Bruno in France and Masaki Yoshikawa in Japan, along with his colleagues, published proofs. Mathematical arguments. They essentially said that, according to the established rules of quantum mechanics and thermodynamics, a time crystal of the kind Wilczek described was impossible. Their argument was subtle but powerful. It came down to that idea of the ground state in something called thermal equilibrium. Let's think about our cup of hot coffee again. When you first pour it, it's hot. The little coffee molecules are zipping around with a lot of energy. The air in the room is cooler. Its molecules are moving more slowly. The coffee and the room are not in equilibrium. But if you leave the coffee on the table, it slowly cools down. It shares its energy with the room. Eventually, the coffee and the room are the same temperature. The system has reached thermal equilibrium. Everything is settled. There are no more grand changes. It's a state of rest, of balance. The ground state of an object is the ultimate state of equilibrium, the state it would reach at the absolute coldest temperature possible, absolute zero. What Bruno and Yoshikawa argued was that in any system at thermal equilibrium, a time crystal cannot exist. They showed, with mathematics as their language, that the ground state of any system must be static. It cannot have things that are oscillating or moving in a regular pattern. Any little blip or motion would eventually be smoothed out as the system settled into its final, quiet, balanced state. Think of dropping a pebble into a still pond. There are ripples for a moment, a beautiful repeating pattern. But soon the water settles, the ripples fade, the pond returns to equilibrium. It becomes still. They argued that a time crystal would be like ripples that never, ever fade away, and in a system left to its own devices, this was forbidden. It was a powerful counter-argument. For a moment, it seemed like the beautiful idea of a time crystal was just a dream, a fascinating mathematical curiosity that couldn't exist in the real world. The book was interesting, the scholars said, but its story was a fantasy. This is a common story in science. An exciting new idea is met with skepticism, and this skepticism is not a bad thing. It's essential. It's the immune system of science, protecting it from ideas that are not robust, that don't hold up to scrutiny. The debate forces everyone to think more deeply, to refine their ideas, to check their assumptions. And in this debate, a key phrase became very important: thermal equilibrium. The proofs against time crystals were all about systems in equilibrium, systems that had been left alone to settle into their final, most boring state. But what about systems that are not left alone? What about systems that are poked, or prodded, or driven? This is where the story takes a turn. The conversation in the great library of physics shifted. The scholars didn't close the book on time crystals. Instead, they started a new chapter. What if we're not looking at a still pond? What if we're looking at a fountain? A fountain is not in equilibrium. Water is constantly being pumped up, constantly flowing. It's in what's called a non-equilibrium state. It's not settled, and it's not supposed to be. It's being driven by an external force, the pump. So, the new question became, could a time crystal exist in a non-equilibrium system? A system that is being continuously nudged by an outside force? This was a much more complicated question. The elegant proofs that said no to equilibrium time crystals didn't apply here. It was a new, unexplored territory. The hunt for the time crystal was not over. It had just moved to a new location, from the quiet pond of equilibrium to the bubbling, dynamic world of non-equilibrium. And it was in this new world that the treasure would finally be found. The year is 2016. The search for the time crystal has moved from the theorist's blackboard to the experimentalist's laboratory. These labs are not like the ones you might imagine from old movies, with bubbling beakers and smoking flasks. They are quiet, clean, and cold, incredibly cold. They are places of extreme precision, where individual atoms are manipulated with lasers and magnetic fields. Think of a watchmaker, but instead of tiny gears and springs, the components are the very building blocks of reality. In two different labs, on opposite sides of the United States, two independent teams were closing in on the prize. They were working separately on different systems, but they were guided by the new theoretical map, the one that pointed towards non-equilibrium systems. At the University of Maryland, a team led by physicist Chris Monroe was working with a string of ions. An ion is just an atom that has a little electrical charge. Imagine a string of tiny microscopic pearls suspended in a vacuum by electromagnetic fields. Monroe's team used ions of an element called ytterbium. They had a line of them, just 10 of them, hovering in space. These ions have a property called spin, which is a bit like a tiny internal magnet. Each ion spin can point up or down. So you have this line of 10 little magnets and they can interact with each other. Their neighbors can influence which way their spin points. The key was how they drove the system. They didn't just leave the ions alone. They pulsed them with a laser, a very precise rhythmic pulse of light. Pop, 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 a steady beat. This laser pulse was the pump from our fountain analogy. It was the external force that kept the system from ever settling into a quiet equilibrium. It continuously added a bit of energy, nudging the spins of the ions. And then they observed something remarkable. They were hitting the ions with this laser at a certain rhythm. Let's call it rhythm A, but the ions didn't respond with rhythm A, the pattern of their spins. Flipping up and down didn't match the laser's pulse. Instead, the spins started flipping in a new pattern, a new rhythm, which was exactly twice as long as the laser's rhythm. If the laser went pop, 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 the chain of ions responded flip, nothing, flop, nothing, flip. It was ticking at half the frequency of the drive. It had developed a life of its own. It had taken the energy it was being given and organized it into a new, stable, repeating pattern in time. It was a time crystal. At the very same time, hundreds of miles away at Harvard University, another team led by Mikhail Lukin was achieving a similar feat, but in a completely different way. It's a wonderful example of how science works. When a discovery is real, it can often be found through different paths. Lukin's team wasn't using a string of ions. They were using a diamond. But not just any diamond. They were looking at tiny imperfections inside the diamond structure. These are called nitrogen vacancy centers. Imagine a perfect honeycomb of carbon atoms, and in one spot, a carbon atom is missing, and its neighbor is a nitrogen atom instead. This tiny flaw creates a unique quantum system, a little island of weirdness inside the perfect crystal. Like the Maryland team, the Harvard team also used a driving force. They used microwave pulses to nudge the quantum states within these diamond imperfections. And just like Monroe's team, they found that the system responded at a different rhythm. They would poke it with a regular beat, and the system would answer back, but at a slower, subharmonic beat. The pattern repeated, but over a longer time period than the poke. It was stable. It was robust. If they nudged it a little bit off kilter, it would find its way back to its preferred rhythm. It was the second confirmed sighting of a time crystal. This was a monumental moment. The book that the skeptics thought was a fantasy turned out to be a true story. The time crystal was real, but it was a different kind of creature than the one Frank Wilczek had first imagined. His original idea was for a crystal that moved in its ground state, in perfect equilibrium. The time crystals found in 2016 were different. They needed that constant nudge, that external drive. They were what we now call Floquet time crystals, or discrete time crystals, named after the mathematical theory used to describe such periodically driven systems. So the discovery didn't prove the original skeptics wrong. Exactly. It cleverly sidestepped their arguments. They were right. A time crystal can't exist in a quiet, settled equilibrium system. But in a driven, non-equilibrium system, the rules are different. And in that noisy, dynamic, constantly poked environment, this strange new phase of matter could finally emerge and show its face. A crystal that keeps time. So, what are these things really? Let's try to build a clear picture in our minds. We know what a regular crystal is. It's a solid with a repeating pattern in space. It breaks spatial translation symmetry. That's a fancy way of saying that even though the laws of physics are the same everywhere, The crystal itself is not. There are atoms here, but empty space next to them. The crystal has a preferred pattern. A time crystal does the same thing, but for time. It breaks time translation symmetry. The laws of physics are the same at every moment in time, but the time crystal itself is not. It has a preferred rhythm. It's in one state now, but in a different state a moment later, and then back to the first state after that. It oscillates. It ticks. But here is the absolutely crucial part, the part that makes it a time crystal, and not just, say, a ticking clock or a bouncing ball. It does this spontaneously, and its rhythm is different from the rhythm of the force pushing it. Let's use an analogy. Imagine you have a big bowl of Jell-O, nice and wobbly. Now you decide to poke it. You tap your finger on the side of the bowl once every second. Tap, tap, a very regular rhythm. You might expect the Jell-O to jiggle in time with your taps. Jiggle, jiggle, jiggle. But what if it didn't? What if you tapped it every second, but the Jell-O decided to do its own thing? What if it only did a big slow wobble every 2 taps? You go tap, tap, and the Jell-O goes wobble, quiet, wobble, quiet. The Jell-O has adopted its own rhythm, which is a fraction of the rhythm you are providing. In this case, half the frequency. This is what physicists call a subharmonic response. And this is the signature, the smoking gun of a discrete time crystal. It takes the energy you're putting in, and instead of just mimicking your rhythm, it organizes itself into a new, more complex, slower rhythm. It's not a random jiggle. It's a stable, repeating pattern. It's as if the collection of atoms has collectively decided on a new dance, a waltz to your polka music. And this isn't just a single atom doing this. A single atom being pushed by a laser might do all sorts of things. The magic of a time crystal is that it is a many-body phenomenon. It's the entire collection of atoms, all the ions in the chain or all the defects in the diamond, working together. They are all communicating, all part of the same collective dance. They are locked in phase with each other. This collective behavior is what makes it a phase of matter, just like a solid, a liquid, or a gas is a phase of matter. It's a new way for many particles to organize themselves. Let's visualize this. Close your eyes for a moment. Picture that string of 10 little glowing ions hovering in the dark. A laser flashes on them, a brief, sharp pulse of blue light. Then another, and another. A steady, quick rhythm. Now watch the ions themselves. In your mind's eye, see their internal spins. Let's say up is green and down is red. After the first flash of the laser, maybe they are all green. Green, green, green. Down the line, the second laser flash comes, but they don't change. They stay green. The third laser flash comes. And now, in perfect unison, they all flip to red. Red, red, red. The fourth flash comes. They stay red. The fifth flash, they all flip back to green. They have created a pattern that takes 2 flashes of the laser to complete one of its own cycles. They are ticking together as one. A tiny quantum chorus singing a song at half the tempo of the conductor's baton. That is the essence of a Floquet time crystal. It's a driven system. It has a subharmonic response. And it's a collective, many-body state. It's not just a weird quirk of one atom. It's a new form of order, a new way for matter to exist, a dance that unfolds not in space, but in time. Now, you might be wondering, How is this possible? What secret mechanism allows a group of atoms to conspire in this way to take an external rhythm and transform it into a new one? The answer lies in a strange and wonderful corner of quantum mechanics called many-body localization. It's a bit of a mouthful, but the idea behind it is surprisingly gentle and easy to picture. Let's go back to our cup of hot coffee. It cools down because the fast-moving coffee molecules bump into the slower-moving air molecules, sharing their energy. The energy spreads out, or thermalizes, until everything is at the same temperature. This is the normal way of things. Energy likes to spread. It's like dropping a bit of food coloring into a glass of water. At first, it's a concentrated blob, but soon it spreads throughout the water until the whole glass is faintly colored. The system reaches equilibrium. But what if the energy couldn't spread? What if the food coloring, once dropped in, just stayed put? This is what many-body localization, or MBL for short, is all about. It's a state where a quantum system is prevented from reaching thermal equilibrium. It's a way of getting stuck. Imagine you are in a very crowded room at a party. It's so crowded you can barely move. You hear an interesting piece of gossip from the person next to you. In a normal, less crowded room, you might move across the room and share that gossip with a friend. The gossip, like energy, would spread. But in this super-crowded MBL party, you're stuck. You can only talk to the people immediately around you. The gossip gets localized. It stays in your little corner of the room and never reaches the other side. In a quantum system, what causes this crowding? The answer is disorder. Not chaos, but a kind of planned messiness. In the Harvard experiment, for example, the nitrogen vacancy centers in the diamond are not perfectly evenly spaced. They are scattered randomly. This randomness in their positions and their interactions acts like the crowded room. It creates a complex energy landscape with lots of little pockets and barriers. When the system is pulsed with energy from the microwaves, that energy gets trapped. It can't flow freely from one part of the system to another. The system can't thermalize. It can't settle down into a boring uniform state. So, this many-body localization is the first key ingredient. It sets the stage. It prevents the system from just heating up and becoming a random mess. It preserves the delicate quantum information. It keeps the dancers in their own little groups, ready to listen to the music. The second ingredient is the drive, the periodic pulse of the laser or the microwaves. This is the music. This constant poking is what allows the system to exist in a special kind of state called a non-equilibrium steady state. It's not in equilibrium, but it's not randomly changing either. It has settled into a stable pattern of behavior in response to the driving. Think of a river. It's never still. Water is always flowing. But the river itself, its shape, its path, can be stable for a very long time. It's in a steady state, but not an equilibrium one. Our time crystal is like a little eddy in this flowing river, a stable, swirling pattern created and sustained by the overall flow of energy. So, the disorder from MBL prevents the system from melting into a thermal soup, and the periodic drive coaxes the localized states to dance together in a synchronized subharmonic rhythm. The combination of these two things is what gives birth to the time crystal. And this phase of matter has a property that is very much like a normal crystal: rigidity. If you take a regular salt crystal and you push on it gently, it deforms a little, but it doesn't break. It holds its shape. It's rigid. A time crystal has temporal rigidity. its rhythm is robust. In the experiments, the scientists found that they could be a little bit imperfect with their laser pulses. They could change the frequency a tiny bit, or make the pulses slightly uneven, but the time crystal didn't care. It stubbornly stuck to its own rhythm. It would keep ticking with its tick, nothing, tock rhythm, even if the driving pulse was a little sloppy. This rigidity is a hallmark of a true phase of matter. It's not a delicate, fragile effect. It's a tough, stable state that can resist small disturbances. It has its own identity, and it wants to maintain it. So the physics behind it is this beautiful interplay. A disordered system that refuses to heat up, constantly nudged by an external rhythm, which then collectively decides to create its own, more stable and more stubborn rhythm. It's a testament to the strange and subtle ways that order can emerge from the quantum world, not in the quiet stillness of equilibrium, but in the heart of a driven, dynamic, and ever-changing system. At this point, a very sensible question should be floating in your mind. If this thing is moving forever, even if it's being pushed, isn't it still getting a free lunch somehow? Doesn't this violate the laws of thermodynamics? These laws are some of the most sacred in all of physics. The first law says you can't create energy from nothing. The second law is even more profound. It says that in any closed system, disorder or entropy always increases. Things naturally go from ordered to disordered. An egg unscrambles itself into a chicken about as often as a cold cup of coffee spontaneously heats up. It just doesn't happen. So, does the time crystal, with its perpetual ticking, break these sacred laws? The answer, you may be relieved to hear, is a gentle and reassuring no. The laws of thermodynamics are safe. The universe is not broken. Let's look at why. First, the perpetual motion part. A time crystal is not a perpetual motion machine of the first kind. That's a machine that would create energy out of thin air, violating the first law of thermodynamics. The time crystal doesn't do this. It's not creating energy. In fact, it needs a constant input of energy from the outside, the laser or the microwave pulses, just to exist. If you turn off the laser, the dance stops. The time crystal melts. It stops ticking and settles into a static, boring state. So, it's not a source of free energy. It's more like an incredibly efficient energy transformer, turning a simple rhythm into a more complex one. Now for the more subtle part, the second law of thermodynamics. This law is about entropy, the inevitable slide towards disorder. A classic perpetual motion machine of the second kind would be one that could take heat from a single source, like the air in a room, and turn it all into useful work, causing the room to get colder. This is forbidden, because it would mean creating order out of disorder, decreasing the universe's total entropy. The time crystal doesn't do this either. And the key is that it's not a closed system. The second law, in its strictest sense, applies to isolated systems that aren't interacting with anything else. But a time crystal is, by its very nature, an open system. It is constantly interacting with a driving laser. Energy is flowing into it, and it's also dissipating energy back into its environment. The whole combined system, the crystal, the laser, and the surrounding universe, is absolutely obeying the second law. The total entropy of the universe is still going up, as it must. The time crystal is a little island of astonishing order, but it creates this order at the expense of creating more disorder elsewhere. It's like building a beautiful, intricate sandcastle on the beach. You have created a very ordered structure, but to do it, you had to burn calories, kick sand around, and disturb the beach. The net result for the whole beach system is more mess, even if one little patch of it looks perfect for a while. The best analogy, and one that scientists often use, is that of a child on a swing. Imagine you are pushing a child on a swing. To keep them going, you need to give them a little push every time they swing back towards you. You are the driving force. The child on the swing is oscillating back and forth in a stable pattern. Is the child a perpetual motion machine? Of course not. They need you, the external energy source, to keep going. Now, let's make the analogy a little closer to a time crystal. Imagine you decide to push the child not every time they swing back, but on every other swing. You give a push, they swing out and back again, and only then do you give another push. You are pushing with a period of 2 swings, but the child is swinging with a period of 1 swing. This isn't quite the time crystal case. Let's flip it. Imagine you are pushing very, very fast. You run up and give a little tap, run back, run up, and give another little tap. A very quick rhythm. But the swing, being big and heavy, can't keep up with your frantic tapping. It ignores most of your taps and only responds to, say, every 4th one, settling into its own big, lazy, slow swing. You are driving it at a high frequency, but it is responding at a low frequency. Its motion is phase-locked to yours, but it's a subharmonic response. This is much closer to what the time crystal is doing. The motion seems perpetual, but it's entirely dependent on the pusher. It generates no energy of its own. It performs no useful work on the outside world. It is simply a stable, resonant state of a driven system. So, while the headline time crystal that breaks physics is a fantastic way to grab attention, the reality is more subtle and in many ways more beautiful. It doesn't break the laws of physics. It reveals a new and unexpected way for matter to live within those laws. It shows us that even in a universe that trends towards disorder, there are hidden pockets where stable, intricate, and time-ordered patterns can exist, sustained by a gentle, rhythmic pulse of energy. The rules are safe, but the playground is much, much bigger and more interesting than we thought. So, having established what these time crystals are, and why they don't send the laws of thermodynamics into a panic, let's take a moment to gather our thoughts and summarize their most essential properties. Let's build a clear mental checklist of what makes a time crystal a time crystal. First and foremost is its temporal order. This is its defining feature. Just as a normal crystal has a lattice structure that repeats in space, a time crystal has an oscillating structure that repeats in time. This is not random jiggling. It is a precise, coherent rhythm, a collective heartbeat of the entire system. Second, and this is what elevates it from a mere curiosity to a true phase of matter, is its robustness. This is that rigidity we talked about. The temporal order is stable against small perturbations. You can mess with the driving laser a bit, make it a little stronger or weaker, or slightly change its timing, and the time crystal will hold its ground. It will stick to its chosen rhythm. This is crucial. It shows that the rhythm isn't just a fleeting coincidence, but an intrinsic, preferred state of the system. It's like a well-made bell. You can tap it with a pencil or a spoon, and while the sound might be a little different, the fundamental note it rings with remains the same. The time crystal rings with a specific temporal frequency, and it's stubborn about it. Third on our list is the subharmonic response. This is the telltale signature that experimenters look for. The system oscillates at a frequency that is a fraction of the driving frequency. Most commonly, it's period doubling, meaning it ticks once for every 2 pushes from the drive. But other fractions are possible, like period tripling or more complex relationships. This is what distinguishes it from a simple forced oscillation, like a flag flapping in the wind. The flag flaps at the same frequency as the gusts of wind. The time crystal, in its quantum wisdom, chooses its own slower beat. It's a non-linear response, a creative interpretation of the driving rhythm. Fourth, this is a quantum many-body phenomenon. You cannot make a time crystal out of a single particle, nor can you make one out of classical objects like billiard balls. It requires a whole ensemble of quantum particles, like the ions in a chain or the defects in a diamond, that are all interacting with each other. Their quantum properties, like spin and superposition, and their collective interactions are what allow this strange state to emerge. It's a group effort. The whole is truly more than the sum of its parts. The individual atoms are the dancers, but the time crystal is the synchronized ballet they perform together. And finally, the time crystals we have discussed and created so far are non-equilibrium phenomena. They are specifically Floquet time crystals, which exist only in these periodically driven systems. They need that constant input of energy to sustain their temporal order. This distinguishes them from the initial, more fantastical idea of a time crystal that would oscillate forever in its true ground state without any external input. The distinction is vital. It's the key that unlocked the puzzle and made their creation possible, and it's the reason they live in harmony with the laws of physics. So there you have it, a checklist for this new state of matter. Temporal order, robustness, subharmonic response, a quantum many-body nature, and a reliance on a non-equilibrium-driven state. These are the pillars that define this fascinating new entry in the Encyclopedia of Matter. The story of the time crystal did not end in 2016. In science, a breakthrough is never an endpoint. It's a doorway opening into a whole new landscape of questions and possibilities. The initial discoveries by the teams at Maryland and Harvard were like the first sighting of a new continent. Now, the age of exploration could begin. And explore they did. Scientists around the world, armed with this new understanding, began to design new experiments and push the boundaries of what was known. One of the most significant steps forward came in 2021 from a place you might associate more with search engines than with fundamental physics: Google. Google has been investing heavily in building quantum computers. These are machines that harness the strange rules of quantum mechanics to perform calculations that are impossible for even the most powerful classical supercomputers. One of their most advanced processors is called Sycamore. It's a chip with 53 superconducting quantum bits, or qubits. A team of physicists, a collaboration between Google, Stanford, Princeton, and other institutions, decided to use Sycamore to create a time crystal. This was a significant step up in scale and complexity from the original experiments, which used about a dozen or so quantum particles. Using a programmable quantum computer gave them an incredible level of control. They could precisely program the interactions between their qubits and the sequence of driving pulses. They programmed the Sycamore chip to mimic a disordered, interacting quantum system, the perfect recipe for a time crystal. They then applied the rhythmic pulses and watched. What they created was the largest and most robust time crystal ever seen. While the first time crystals survived for a few dozen cycles of their tick-tock rhythm, the one on the Sycamore processor lasted for hundreds of cycles before the delicate quantum state was lost. It was a stunning demonstration, proving that time crystals were not just a niche phenomenon in a few specific physical systems, but a general phase of matter that could be realized and studied in a controlled, programmable way. It was as if the first explorers had only seen the coastline, and now Google's team had drawn a detailed map of a whole region inland. This work also highlighted the contributions of a new generation of theorists who had laid the groundwork for these advanced experiments. Scientists like Vedika Kamani, then at Harvard, and Shivaji Sandhi at Princeton, along with their collaborators, had been instrumental in developing the theoretical framework of flow-K phases and many-body localization, providing the very recipes that the experimentalists were now following. Science is always a dialogue between theory and experiment, a dance between the thinkers who imagine what could be and the builders who find a way to make it real. But the explorations didn't stop there. Other new types of time crystals began to emerge from the theoretical mists. One fascinating idea is the prothermal time crystal. This is a subtle and beautiful concept. Remember how many-body localization, the system being stuck and unable to heat up, was a key ingredient? Well, it turns out you don't always need true, eternal localization. Some quantum systems, even without strong disorder, can enter a state that looks and acts like a time crystal for an incredibly long time, but not forever. They exist in a pre-thermal state, a long-lived, stable state that only eventually, after a time that can be exponentially long, gives way and thermalizes. For all practical purposes, it is a time crystal. It might tick away for longer than the age of the universe before it finally melts. This discovery broadened the range of systems where time crystals could be found, suggesting they might be even more common in nature than we first thought. And then, theorists proposed an even more exotic variant, the clean flow-K time crystal. The first time crystals required disorder, that planned messiness, to prevent the system from heating up. But new theories suggested that in some special cases, you could get a time crystal even in a perfectly clean, ordered system. This could be achieved by using long-range interactions between the particles, allowing them to coordinate their dance without the need for the crowding effect of disorder. This is still a frontier of research, pushing our understanding of how quantum systems can self-organize. Each of these discoveries, from the Sycamore experiment to the theories of prethermal and clean time crystals, adds a new layer to the story. They show that this is a rich and vibrant field of physics. The time crystal is not just one thing. It's a whole family of phenomena. We are just beginning to meet all of its strange and wonderful relatives. The map of this new continent is getting bigger and more detailed with every passing year, revealing new rivers, new mountains, and new forms of life we never dreamed were possible. With every new discovery in fundamental science, one of the first questions we ask is, what is it good for? It's a natural human question. We are tool makers, problem solvers. We see a new phenomenon, and we wonder how we can use it. The time crystal, this bizarre, forever-ticking phase of matter, is no exception. While the technology is still in its infancy, a dream on the horizon, scientists can already see the shimmering outlines of potential applications that could, one day, revolutionize our world. Perhaps the most exciting potential application lies in the field of quantum computing. One of the greatest challenges in building a quantum computer is the problem of decoherence. Quantum states, the qubits that store and process information, are incredibly fragile. The slightest vibration, a stray magnetic field, or a change in temperature can disrupt them, causing them to lose their quantum information. It's like trying to write a message on the surface of a pond. The slightest breeze will ripple it away. This fragility is what limits the power of today's quantum computers. This is where the robustness of a time crystal could be a game changer. Remember how a time crystal is rigid? How it stubbornly holds on to its rhythm, even when things are a bit messy. This same property could be used to create an incredibly stable quantum memory. Imagine encoding quantum information not in a single fragile qubit, but in the collective oscillating state of a time crystal. The information would be stored in the phase of the crystal's ticking, in the synchronized dance of all its particles. Because the time crystal is a robust, many-body state, it would be naturally resistant to the small errors and disturbances that plague individual qubits. It would be like carving your message in stone instead of writing it on water. A time crystal-based quantum memory could protect information for much longer, paving the way for more powerful and reliable quantum computers. Another fascinating possibility is in the realm of precision timing. We already have incredibly precise atomic clocks. They are the bedrock of our GPS systems, our financial networks, and our scientific experiments. These clocks work by locking a laser to the natural, consistent frequency of electrons jumping between energy levels in an atom. But a time crystal offers a new kind of timekeeper. It is a system of many interacting particles, all locked to a single stable frequency. This collective nature could make it even more resistant to noise than a standard atomic clock. A clock based on a time crystal might be so stable, so precise, that it could be used to detect the faintest, most subtle signals in the universe, like the tiny ripples in space-time known as gravitational waves, or even to search for the mysterious substance known as dark matter. Time crystals also provide a unique playground for scientists themselves. They are a perfect laboratory for studying one of the most challenging and mysterious areas of modern physics: non-equilibrium quantum dynamics. That's the study of how complex quantum systems behave when they are far from their comfortable, settled state. This is a wild frontier, and we don't have many tools to explore it. Time crystals are like a perfectly preserved specimen from this wild land. By creating them and studying their properties, we can learn the fundamental rules that govern the behavior of matter and energy in these extreme, dynamic conditions. This knowledge might not lead to a new gadget tomorrow, but it deepens our fundamental understanding of the universe, which is the wellspring from which all future technologies flow. Finally, just by expanding our definition of what a phase of matter can be, time crystals open the door to designing entirely new materials with exotic properties. If we can have order in time, what other strange forms of order might be possible? Could we design materials that conduct electricity in new ways, or interact with light in ways we've never seen before? Understanding the principles behind the time crystal, the interplay of driving, disorder, and quantum interactions, gives engineers a new set of tools and a new way of thinking. It could lead to breakthroughs in electronics, photonics, or materials science that we can't even imagine yet. The journey from a theoretical idea to a world-changing technology is a long and winding one. But the potential is there, a quiet promise sleeping within this strange ticking crystal. A promise of more powerful computers, more precise clocks, and a deeper, more complete understanding of the fabric of reality itself. It is important, as we drift on these currents of exciting possibility, to keep our feet gently touching the ground. The dream of time crystal technology is beautiful, but the path from today's laboratories to tomorrow's applications is long and filled with challenges. It's good to be aware of the hurdles, not to be discouraged, but to appreciate the incredible ingenuity it will take to overcome them. The first and most significant challenge is the environment they require. The time crystals we have created so far are incredibly delicate creatures. They can only exist under extremely controlled conditions. They require ultra-low temperatures, just a fraction of a degree above absolute zero. At these temperatures, the chaotic jiggling of thermal energy is calmed to a near standstill, allowing the subtle quantum effects to emerge. Creating and maintaining these cryogenic conditions is complex and expensive. They also need to be almost perfectly isolated from their surroundings. A stray bit of sound, a tiny fluctuation in the magnetic field, or even a single photon of light coming from the wrong place can be enough to shatter the delicate temporal order. The time crystal needs a quiet, dark, stable home to perform its rhythmic dance. This makes building a practical device out of one a monumental engineering task. You can't exactly put a time crystal-powered memory stick in your pocket if it needs a room-sized refrigerator and a vacuum chamber to work. Another limitation is their very nature as quantum systems. The effects we've discussed are all happening on the microscopic scale of atoms and their spins. Scaling this up to a macroscopic device that you can hold in your hand is a leap of incredible magnitude. We are getting better at controlling dozens or even hundreds of quantum particles, as the Google experiment showed, but building a system with the billions upon billions of atoms needed for a conventional electronic device is far beyond our current capabilities. And while the coherence times, the length of time the crystal can maintain its ticking before it melts, are improving, they are still finite. The Sycamore time crystal lasted for hundreds of cycles, which was a huge achievement, but it was still just for a fraction of a second. For a quantum memory to be truly useful, it needs to store information for much, much longer. Scientists are working on ways to protect these states, to actively correct errors and extend their lifetimes, but it remains a central area of research. These challenges are not roadblocks, they are frontiers. They are the mountains that the next generation of scientists and engineers will learn to climb. Every great technological leap, from the steam engine to the microchip, once seemed impossible. They all required overcoming fundamental limitations through decades of patient, brilliant work. The story of the time crystal is still in its very early chapters. We have discovered a new and wondrous phenomenon, a new continent on the map of physics. We have taken our first tentative steps onto its shores and seen the strange and beautiful landscape. The great work of exploring it, of understanding it, and perhaps one day of building with it, has only just begun. And so, our journey into the heart of the time crystal comes to a gentle close. We began with a simple, elegant question. If a pattern can repeat in space, can it also repeat in time? We followed that question from the mind of a theorist, through the debates of the skeptics, and into the quiet, cold laboratories where it was finally made real. We've seen that these are not magical perpetual motion machines, but a subtle and profound new phase of matter, born from the strange rules of the quantum world. They live in a state of constant, driven motion, a stable dance that resists the slide into chaos. They are a testament to the fact that order can be found not just in stillness, but in rhythm, not just in equilibrium, but in a steady, life-giving flow. Close your eyes and picture it one last time. A vast, dark, quiet space. And in that space, a collection of tiny points of light. A laser pulses a silent, steady beat. And the points of light respond. They begin to glow and fade in unison, but at their own pace, a slow, majestic, and unshakable rhythm. A heartbeat in the void, a clock built from the very fabric of reality. It is a reminder that the universe is not only stranger than we imagine, it is stranger than we can imagine. And there is a deep and soothing peace in that knowledge. A peace in knowing that there are always new wonders to be discovered, new forms of beauty to be found, and new quiet rhythms waiting to be heard, just beneath the surface of things. The universe is ticking with secrets, and we are just learning how to listen. Sleep well.